Hello students, hope you all are doing well. Here in this video, we are going to present you the very first topic or very first lesson in the bonding. It's the unit 2 in chemistry, A-level chemistry, bonding and structure. It's already we had an overview regarding this unit, bonding and structure. You could call that the introduction video. In our earlier video, we have already found out that what are we having? In this unit, we are having bonding and structure. First, we are going to talk about all the possible types of bonding. Then secondly, we are going to talk about the structures they form after being bound with those bonding. What are the all possible types of bonding? You could categorize them into two types as prime type and secondary type. Primary types are the strong type of bonding. They form those structures, molecules and lattices, are covalent, ionic and metallic bonding are the strong type. Then it's with respect to these, the secondary type, we call them intermolecular attractions. Attractions for the reason it's not strong as much as of those prime type of bonding. Therefore, these are quite slight attraction forces only. You get being evolved between those structures, those have already formed, being bound with these prime types. Means these could be found, these secondary type of attraction forces could be found between two molecules or a molecule with an ion. So those there are 5 types of those. Those are ion permanent dipole, permanent dipole, permanent dipole, ion induced dipole, permanent dipole, induced dipole, and induced dipole, induced dipole. Then those prime type, we call them intramolecular bonding as well. Those are, as already you know, covalent, ionic and metallic. Anyway, all of these bonding and attraction forces, for all of them, there is one common thing. Student, if it's a bonding, you would all the times find an attraction evolved. Where would you find attraction being evolved? It's students, always you would get an attraction being evolved between two oppositely charged species. Yes. It's between two opposite charges only. All the times you would get an attraction. If there is a bonding, you need to have two oppositely charged species. It's the fundamental of all these, for all these bonding. It is the fundamental, not mental. It's the fundamental for all these bonding is, if it is a bonding, you need to have an attraction evolved between two opposite charges. If they are alike charges like plus and plus or minus and minus, they would get repelled for sure. Students, if they are plus and minus only, always you would get an attraction force. Isn't it? Isn't it having that all the times, even in the society? Those attraction evolve between opposite charges, right? Okay. So students, here we are going to talk about the very first type of bonding. So it's the covalent bonding or covalent bonds. What is a covalent bond? So it's you might have already learned this even in your O-level life. A covalent bond, when someone asks you the question what is a covalent bond, you would proudly say sharing electron. A covalent bond is formed. Okay, that's good. That's a good answer. If you haven't got that already, to say that sharing electron, a covalent bond is formed. It's okay. But students, could you show me the attraction there in that answer? If it is a bonding, you need to be able to explain that there is an attraction evolving. Then if you have got to say that sharing electron, a covalent bond is formed, could you show me the attraction force there in that answer? It's quite like not really showing the attraction, right? They are inside that arm, so you can't find any finite attraction for stating. Okay, anyway, we could still accept that answer as standing for the explanation or definition standing for bonding. Sharing electron, a covalent bond is formed. But seeking for the attraction, still I have a doubt. When I am truly kind of seeking what truly a covalent bond is, where is that the true attraction force you get there? Then if someone has got to tell me sharing electrons, covalent bonds are formed. Okay, it might be the way how covalent bonds are formed, but where is the attraction? If that fellow has still got to say that sharing electrons, covalent bonds are formed, then it's quite like there is a contradiction between my expectation and that answer, as that fellow has learned that the way how covalent bonds are formed, it's sharing electrons all the times. Then what I have here the thirst for is truly seeking where the attraction force is. Then to me it's quite like I'm asking what is the covalent bond, where is the attraction force? Then that answer is quite like it's how the attraction force or covalent bond is formed is sharing electron. Then when we seek for truly where this true attraction force actually evolve, when they share electrons forming a covalent bond, it's then you need to go to the very beginning, means origin, means let's find it out. Before share electrons by those atoms, you have electrons there inside the shells of atoms. There you find electrons in shells. Electrons are filled into shells of atoms, energy shells. Then in energy shells further, you could find these electrons out. They are in subshells. In first shell you have 1s. In second shell 2s, 2p. Third shell 3s, 3p, 3d. Fourth shell 4s, 4p, 4d, 4f. Such subshells you have got these electrons being filled. Then if you have already followed that the electronic configuration and build-up principle, we call that Aufbau principle, how the electrons are filled into those subshells is the increasing order of subshells energy. So anyway, in subshell, within subshells, the most probable places, areas that you find an electron being is called, is referred as an atomic orbital. Within a subshell, you would have one such region. It is spherical in shape. It's called S atomic orbital. Then within P subshell, you have 3 of such regions being perpendicular to each other. Those are dumbbell shaped. We call them P atomic orbitals. In D subshells, you have 5 such double dumbbell shape. We call them D atomic orbitals. In F subshell, you have 7 of such atomic orbitals with complex shapes. We call them F atomic orbitals. Here the point is, electrons, when they get filled into an atom, electrons are filled in shells. Inside shells you have subshells. Inside subshells you have atomic orbitals. So therefore, it is electrons are filled into atomic orbitals in subshells in shells, isn't it? Okay, students. Therefore, when these atoms are about to share electrons, you could first find those electrons being there in their atomic orbitals. Then you could find it out the outermost shells atomic orbitals. Means when you consider the outermost occupied shells, it would have subshells. It would have atomic orbitals. So electrons, when they are about to share, you would find that out electrons being there in their atomic orbitals in subshells in shells. Then students, when they are about to share electrons, they need to do something like they need to overlap their atomic orbitals. Okay, so let me show you that. If it is you have atom A having an atomic orbital with one electron, single electron. So if you have got another atom named B, it is the nucleus, this dot. Then having another electron, one electron, single electron. If these both kind of talk each other as, shall we share our electron? Okay, let's share. So how could we share electrons? Let's overlap our atomic orbital. Okay, then they would overlap their atomic orbitals. This is the overlapping. We call it overlapping. Okay, they overlap. Then they would keep those two electrons earlier were there in own atomic orbitals. Now in this overlap orbital. Students, what is the overlap orbital is called? It's after overlapping, they are about to form a molecule. Therefore, students, if we could identify this common orbital now as the molecular orbital. Okay, molecular orbital. So, students, in their effort to share electrons, they have got their electrons in atomic orbital. So, when they are about to share electrons, it's their first overlap their atomic orbitals as to form a molecular orbital. Then they keep those common electrons, sharing electrons, they are inside the molecular orbital. Okay, that's how the story begins. When they share electrons, they overlap their atomic orbitals, forming a molecular orbital. Then students, as I have already told you, if it is a bonding, you need to have an attraction force. All the times attractions are evolved between two oppositely charged species. Here as well, though it's a covalent bonding, though they share electrons, they are also, you could find an attraction, electrostatic attraction force evolved. How? Students, this nucleus is having, an atom's nucleus is having protons. What else? And neutrons as well. Okay, this atom also got a nucleus, so is having protons and neutrons there. So the protons are positively charged, therefore this electron cloud is the common electron cloud, is the shared electron cloud, would be attracting this nucleus towards that with a force. It's an electrostatic attraction force. Then the same electron cloud would be attracting the other nucleus as well. Then these red colored arrows are denoting, means standing for the electrostatic attraction inserted by this common electron cloud towards their nuclei of two atoms. Students, these electrostatic attraction forces evolved is the covalent bond. So then it is the electrostatic attraction force evolved between the electron cloud held there in the molecular orbital after overlapping of those atomic orbitals. Then that electrostatic attraction force inserted by that common electron cloud towards two nuclei. That's the covalent bonding. Hope you could understand that. Again, so covalent bonding simply is a sharing of electrons. When they share electrons, before sharing, they have electrons in atomic orbitals in subshells in shells of atoms. When they have got their outermost shells having subshells, having atomic orbitals, having electrons to be shared, they first overlap their atomic orbitals, forming a molecular orbital. There would be a molecular orbital having a common region for both, bearing those electrons to be shared. Then that electron cloud would insert an electrostatic attraction towards the two nuclei of two atoms. That electrostatic attraction force is referred as the covalent bonding. Okay. Then students, it's the next point that we are going to pay our attention on is whether all the atomic orbitals, all the type of atomic orbitals could overlap in this manner as to form covalent bonding or not. What is that? Means it's not based on their shapes, like S subshell would have spherical shape S atomic orbital. P subshells would have dumbbell shape P atomic orbitals. There would be 3 of them within one P subshell. D subshells would have double dumbbell shaped D atomic orbitals. There would be 5 of such D atomic orbitals within one D subshell. F subshells would have 7 of F atomic orbitals having their electrons. It's not about their such type, like whether SPDF, whether the shape is spherical, dumbbell, double dumbbell, or such complex shapes standing for F. But it's now about how many electrons you have got there in those atomic orbitals going to overlap. So based on the number of electrons, if you could remember Pauli's exclusion rule, it's there you learn the maximum number of electrons could be kept in any orbital is 2, the least is 0. Okay, then students, based on that, if I draw it in this way, one atomic orbital, it's you could recognize 3 types of atomic orbitals based on the number of electrons that those would have. Having no electrons, it's let's call empty atomic orbitals. So it's an orbital here, having no electrons. So it could have one electron. Let's symbolize the electron here in this way, half arrow. So it is then the other could have 2 electrons in this way, 2 arrows in 2 opposite directions. It's the Hund's rule, right? Subshell would be first filled their atomic orbitals as singly, means first all the atomic orbitals within one subshell would be filled as with 1 electron in one direction. So secondly, then those after filling those all atomic orbitals with single electron, secondly they would start being paired. Okay, the other type is, we call this pair. This is single, or we could then call based on that, if this is paired, this is, if this is paired, this is unpaired. Okay, so atomic orbital. Here on, we are going to talk about these 3 types of atomic orbitals. Using those 3 types, let's find it out various possible combinations that we could consider whether it's possible or effective overlapping that they are going to make, or non-possible, or let's say impossible overlapping that they are going to make. How could we recognize whether it's a possible or non-possible overlapping? It's a very good question. Students, when you check for an overlapping, if you find, let's say for an example, after overlapping, it's if you find some electrons there, this is the molecular orbital. So there would be some possible attractions and repulsions here. This nucleus is having positive charge. This nucleus also is having positive charges on it, in it. So then those 2 nuclei, positive to positive, plus to plus, they would repel each other. Then this positive charge would be attracted towards this electron cloud. There would be an attraction evolved between the electron cloud and electron cloud in the molecular orbital and the positive charge in the nucleus, and here also there would be a repulsion evolved between allied charges, positive charges in the nuclei, then there will be another repulsion could evolve between those electrons in the molecular orbitals. So with increase of the number of electrons, molecular orbitals, electron repulsion would get increased. So normally, according to Pauli's exclusion principle, it is stating that maximum number of any orbital could have having least repulsion or could exist there is 2. So the maximum number is 2. When it exists, there would be a extra repulsion, very high repulsion evolving among those electrons in the orbital. Therefore, students, it's not stable. It's going to be very unstable due to the repulsions evolved if you have more than 2 electrons within any orbital, including this molecular orbital. Then its nuclei, they repel each other, electrons, they repel each other, then electrons to nuclei are attracted each other. So when you have got a chance there, as the repulsions are overcome or suppressed by the attractions, then only there would be an effective overlapping possible. Otherwise, all the other times, if the repulsions are greater than of attractions, those overlappings would not be effective. It's not possible overlapping going to be impossible. So let's then find it out which overlappings between these empty, unpaired and paired atomic orbitals, which overlappings are effective and non-effective, impossible. Okay, students, let's first talk about the empty with empty. Empty atomic orbital with empty atomic orbital. If they overlap, in the molecular orbital you won't get any electron being shared. Then it's only the repulsion between 2 nuclei you would get. If there are the repulsions you have, then it's no point of having an overlapping, forming bonding. Therefore, it's not going to ever happen. The point is, an empty atomic orbital of one atom would not overlap with another empty atomic orbital of another atom. It's not possible. Okay, then you might have got the point. Then, students, it's you could then start having different combinations, checking whether those are possible or not. When you think about, check for the overlapping between unpaired atomic orbital with still empty atomic orbital. Then after overlapping, if it is possible, after overlapping, in the molecular orbital there would be one electron only carried. That single electron would insert an attraction force towards each nuclei, but that single electron's attraction force would not be enough to overcome the repulsion force evolving between 2 nuclei. There you are going to have a greater repulsion force than the attraction force, therefore it's not a possible overlapping you are going to have here. So it's not possible. Then students, it's our next combination. We are going to check, keeping here the empty atomic orbital. So we are going to check whether a paired atomic orbital could overlap with an empty atomic orbital. So if they overlap, they would be having 2 electrons kept. They are in the molecular orbital. If it is 2 electrons, it's no matter, they could attract those 2 nuclei, suppressing those repulsion or being that attraction force being greater than of the repulsion possible. The repulsions possible are the repulsion between 2 nuclei as well as repulsion between 2 electrons. So the attractions would be greater than of repulsions when you have 2 electrons in the formed molecular orbital. Okay, therefore it's a overlapping. This is our first possible overlapping that we could find out. Let's check for other combinations as well. So all the possible combinations with empty atomic orbitals we have considered. So the next one is for, let's use here an unpaired atomic orbital and with another unpaired empty we have already taught. So it is unpaired atomic orbital with unpaired atomic orbital. Then if they overlap, they are going to result 2 electrons in the molecular orbital. It's therefore an effective overlapping, possible overlapping, let's call it. So it's the attraction would be greater than of the repulsions. So when you have 2 electrons always after overlapping, when you have 2 electrons being held there in the molecular orbital, those would be permitted. Those will be possible overlappings. What else are the combinations we could consider? Students, it's next having an unpaired atomic orbital with unpaired we found out a paired atomic orbital. So if they overlap, they need to keep 3 electrons, which is greater than of 2. You can't keep 3 electrons in the molecular orbital for the reason then the repulsions between electrons would be greater than of the attractions. Therefore, students, it's not going to be a possible overlapping. So the last is checking for whether it's possible paired with pair. These kind of overlappings. So then it's going to further exceed the number of electrons. It's not 2 now, it's in the molecular orbital there will be 4 electrons kept. It's very high repulsions you are going to have there. Therefore, it's not possible. Its repulsions will be greater than of attractions. Then students, in this way, it's when you have in the molecular orbital having 2 electrons, only the orbitals overlap being permitted, possible. So it's we could then ignore all these combinations, means paired, unpaired, and empty, then empty unpaired, all would not be possible overlapping, not be effective overlapping, but these, a paired with empty as well as unpaired with unpaired, are the possible overlapping. Those would result covalent bonding. Then students, in the applications, this covalent bonding is referred to be, it is both electrons are given by one atom only, one atom's orbital only. So therefore we call that the donor atom. It's the donor atom. So this is going to participate in bond formation just providing an atomic orbital. It's empty. It comes with an empty atom, means empty atomic orbital. So this then a donor, this is the acceptor atom. So then it is you could once think of that in the way like this with 2 electrons on this empty. This first gives 1 electron there on that one. Let's say this is A, this is B. This donates 1 electron there to B. So gaining that electron, this becomes then single. Then it is a 1 electron here you have. So it is then this has donated. So this becomes plus. This has taken. This becomes minus. So you get the negative. This covalent bond being formed now in this normal way, having 1 electron, it's 2 electron. But then we denote it giving a plus charge here, minus charge there. Means it's if we draw a line just to show it's a bonding, then it is with the line it is a plus charge and minus charge. plus 1 and minus 1. At those two atoms, donor is having a plus charge, acceptor is having a minus charge. So this covalent bond type is identified as dative covalent bonds. Our students, so we call it dative covalence. But anyway, after formation of this bonding, after sharing of these two electrons, you can't recognize whether it's a dative covalent or the other type of covalent. It's anyway both are the same. Both covalent bonds are the same after formation. But based on the very first approach, as whether both electrons are given by one atom and other comes with an empty atomic orbital, or both atoms are coming with single electrons, based on that fact, we could call this, when one atom is bringing both and other comes empty, we could call this dative covalent. It's be identified as dative covalent. Then students, with respect to that, this is the normal way of forming covalent bonding, so we call that normal covalent. But it is just a way they identify those two different types or two different approaches of covalent bonds formed. But students, it's actually you can't recognize after formation of these two types as whether it's a dative covalent or normal covalent. Just seen at the bonding means just these both bondings are the same. They are sharing electrons. That's only. So then it's how we could talk about based on the type of atomic orbitals going to overlap. Whether based on the fact whether it's empty or unpaired or paired atomic orbitals that going to overlap, forming covalent bonding. If we could categorize them as possible, impossible. Only possible two overlappings are paired with empty and unpaired with unpaired. All the other overlappings are impossible, not possible, not permitted. So it's you don't need to by heart this. It's easily you could understand if you start seeing this or thinking on them as after overlapping those atomic orbitals, whether you would get 2 electrons all the times in the molecular orbital. If it is 2 electrons you are finally having, then it would be permitted. It would be a possible overlapping. All the other overlappings would not be possible. So students, the next way of categorizing that you could categorize these is based on the type of atomic orbitals involved based on their shapes, or let's call you have atomic orbitals in subshells. So which subshells atomic orbitals are overlapped? Based on that fact also you could categorize those different type of bonding, covalent bonding or molecular orbital being formed in this way. Students, it's possible S orbital to overlap, spherical shaped S orbital to overlap with another S orbital. For an example, it is H2. H is having 1s1, the electronic configuration. So 1s would be overlapped with 1s here. Overlapping those would form a molecular orbital in this way, having 2 electrons. It is then SS overlapping. It's one type of possible, means one type of overlapping that you could categorize. It has SS overlapping when one S is overlapped with another S of other atom. It is SS overlapping. SS overlapping. So students, the form 1 is the SS molecular orbital. SS molecular orbital. So the same SS molecular orbital would be presented in the form of this. Is a swollen place here, the molecular orbital. So SS molecular orbital. Then student, it's another, then you could imagine the other possibilities. A S orbital could be overlapped with a P orbital. P. It is then SP overlapping. SP overlapping. So for an example, you would get HF. H is having 1s1, F is having 1s1, 1s2, 2s2, 2p5. So those 2p5 could be found in the form as 1, 2, 3, 4, 5. So 1 would be unpaired. That unpaired one could overlap with the S1s1. So then the molecular orbital could be referred as its students SP molecular orbital. So this is the SP overlapping. So the same thing could be given in this way as well. Okay, so there are some other atomic orbitals as well. P with P, D with P, S with D, D with D, F with F, F with D. So various different overlappings are possible. So then for the last time we will give you another one overlapping. It's the PP overlapping. Then students, when it is PP overlapping, it is one P need to overlap with another P. So example is F2. F is having 1s2, 2s2, 2p5. So similar here. So unpaired one p atomic orbital there of one of F atom could overlap a p atomic orbital having unpaired electron of the other F fluorine. So then the molecular orbital simply could be shown in the form as of this, having those two electrons there. It is the PP molecular orbital. Same thing could be shown in this way as a swollen place. Here, PP molecular orbital. Then those are the different molecular orbitals formed based on the atomic orbitals who are going to overlap with. Okay students, then if you would find out another different type of overlapping, it's now when you have based on fact, when you have an overlapping on the line that link two nuclei. For an example, it's already we have looked into this. It's H2. It is having 1s1, one hydrogen. So this is 1s1, and this is the other S, 1s1, 1s1. If they are overlapping in this way, these common two electrons are held there, kept there on the line that links two nuclei. So if you are having your overlapping being done on the line that link two nuclei, we call such overlappings are linear overlapping. It is on the line, linear overlapping. Then what is the other type? Other type is when you have got between two atoms, when you have got more than one bond being formed between two atoms, when one overlapping is done, it would be for sure on the same line that link two nuclei. But how would it be the other overlapping? Once when already a linear overlapping has done, Let's find it out. Students, it's next. Let's consider the example O2. That you have a double bond between O and O. Two oxygens. Okay, it's you are going to form two bonds there. So one oxygen is having 1s2, 2s2, 2p. It's 4. So 2p subshell could be given in the form as having 3 of dumbbell shapes atomic orbitals in the XYZ axes in the Cartesian plane. So it's you could call them this is y-axis or py, this is z-axis pz, so this is the x-axis px, so px, py, pz. On those three axes, those lie perpendicular, one perpendicular to other. So those three would be perpendicular to each other. Is how those p atomic orbitals you would find they are out. Then students, it's in oxygen, it's you could find 1, 2, 3, 4. If they are having 4 electrons, as 1p would be paired, other 2 of p's would be unpaired. So both oxygen there would be the same. So when they are about to overlap, they are atomic orbitals. So the first overlapping, this is before overlapping. First overlapping would be having here between these two. Let's place those pair here. So single. It is one oxygen, this is the other oxygen. So students, it's the very first overlapping would take place there between these two on the same line. It's on the same line that link two nuclei. So this is one nucleus, this is the other nucleus. So these are the two nuclei. So is the line. So the first overlapping is having they are on the line that link two nuclei. So you have the common electron, two electrons held here and there. It's the first overlapping. This is the linear overlapping. Linear overlapping. So then, based on the fact whether two atoms are having their overlappings on the same line that link two nuclei, it's we identify those differently as one is linear overlapping. If the overlapping is having on the same line that link two nuclei, let's say you have those P, P, P perpendicular to each other. Other oxygen has got P, P, P perpendicular to each other. One is overlapping on the same line link two nuclei. So here and there you have two unpaired atomic orbitals. These would bend towards each other and overlap at a side to this line. So at the side of this line, so it is we call laterally. They overlap laterally. So if you could denote that lateral overlapping just drawing a line here, or otherwise when you have got one overlapping in this way, the lateral overlapping you could show in the form as of this. This is the linear overlapping. This is the lateral overlapping. This is the lateral overlapping. You could symbolize that lateral overlapping just drawing a single line. Yeah. So students, it's the second type of overlapping. We call it lateral overlapping. So it always having when it is more than one bond formed between two atoms. If it is one bond formed between two atoms, if it is one covalent bond, then it would be always a linear overlapping. If it is more than one bond going to be formed, more than one, it could be maximum 3. The number of bonds could be formed between two atoms. Okay, so then the first overlapping anyway would take place between two atoms linearly. When once they have got in their overlapping being linear, the other all overlappings are not possible on the same line. So the other overlappings are having laterally. So those are called lateral overlappings. Students, it's once when you have already got the linear overlapping, the other all overlapping would take place laterally. Then how would it be? The strength of these two bonds. Anyway, if it's a linear bond means linear overlapping, this electron cloud would attract this nucleus as well as this nucleus straightly. They attract two nuclei straightly towards the electron cloud. So those two nuclei are not attracted, towards each other. Therefore, these linear overlappings form strong covalent bonding. Then students, when it's about lateral overlapping, let's denote it with a different color. Your electron cloud would be held here. So this would be attracted towards that. This would be attracted towards that with a force, attraction force. Then when you think about their attraction each other, if one atom A is attracted there in this direction, if the other atom is attracted there in this direction, let's say with forces F1, F2 or same forces, so then their attraction towards each other, it's just this vector. You get it's if this angle is theta, it is in physics you could learn that it is F cos theta. F cos theta is the attraction of that its vector in this direction. So here also it is F cos theta, means it's not going to be the same F. It's going to be quite lesser than of that F. My point is, if these are attracted towards a point or place, position, here they are laterally, then their attraction towards each other would be quite lesser than as of this linear overlappings attraction. Here linear overlappings are having or causing or inserting the attraction. Finally, they are having or they are attracting each other towards each other on the same line. Therefore, they are attracted straightly each other. It's a strong covalent bond that you get by a linear overlapping. With respect to that, the lateral overlapping, the covalent bond you get by the lateral overlapping would not be that strong. It's just a part of that. Only they experience each other as the attraction they got between each other. So students, therefore, linear overlappings form strong covalent bonding. Then once when you have got a linear overlapping only, it's possible you to have a second choice for next overlapping, lateral overlapping. Then all those lateral overlappings are weaker than of, their attractions are weaker than of the linear overlapping's attraction. Then in this double bond, one is strong, one is weak. The linearly overlapped bond or bond formed by overlapping linearly is the strong one. The bond formed by overlapping laterally is the weak one. Then students, that strong one that you have got overlapping linearly is called the sigma bonding. The other bond, the weak one, that you have got formed overlapping those orbitals laterally, called pi bond. So this is sigma, we symbolize it with this sigma sign. It's a Greek letter, so this is pi. So we symbolize it with the pi, Greek letter. So that's why. Then it's when we have what? Two overlappings being done, or it's between two atoms. When it is more than one overlapping being done, one would be for sure linear overlapping would be the strong one. It is the sigma bonding formed. All the other overlappings would be lateral overlappings, which would be quite weaker than of that sigma bonding. The bond formed is called a pi bond. Pi bond. So when we check for nitrogen, in N2 nitrogen molecules, you have between two ends you have a triple bond. Let's find it out how this triple bond in N2 formed. Between two ends you have a triple bond. For one end it is 1s2, 2s2, 2p3. The electronic configuration. Then students, it's this nitrogen could be shown in the form, its p orbitals could be shown in the form of this having 1, 2, 3 unpaired atomic orbitals, unpaired p atomic orbitals there. Then students, when one nitrogen is having those unpaired atomic orbitals 1, 2, 3, when it is about to overlap with another nitrogen's unpaired p, so 1, 2, 3, the first overlapping would take place on the same line that link two nuclei. It is the linear overlapping. This is the linear overlapping. So all the other overlappings would take place laterally at a site that link two nuclei. It's a linear overlapping. Then if you are going to have these two being overlapped laterally, these two being overlapped laterally, those three p orbitals are perpendicular to each other. First overlapping would take place on the same line that link two nuclei. So it's a linear overlapping, it's a strong bond, strong covalent bond, it's a sigma bond. The other overlappings would take place bending them towards each other laterally. Then other also would be bending them towards each other laterally is the way. So students, these are lateral overlappings. These are lateral, so form pi bonds. This is the linear overlapping, form sigma bonds. Therefore, based on their way of overlapping, whether it's linear or lateral, you could recognize two different types of covalent bonds being formed. One is the sigma bonds formed overlapping linearly. Other one is pi bond formed overlapping laterally. So, hope you could understood these things. So, students, it's the stuff or the content that you have got there under covalent bonding. You have already seen that overlapping those atomic orbitals having a common electron cloud there, the electrostatic attraction force that common electron cloud inserts towards those nuclei is called the covalent bonding. Simply you could call sharing electrons the covalent bond is formed. Then it's based on the type of atomic orbital involved. In covalent bond formation, you could find that unpaired empty, unpaired and empty pair only were the possible overlapping could be made. Then based on the substance type, you could find when they overlap truly, you could find SS overlapping, TP overlapping, SP overlapping being done. Then here finally, based on the fact whether those get overlap on the same line that link two nuclei or laterally, you could find out lateral overlappings and linear overlappings. Linear overlappings form strong covalent bonding while lateral overlappings form weak covalent bonding. Those strong are called sigma bonding, weak are called pi bonding. Okay students, that's what we have got regarding covalent bonding. So, if you are going to round up there here in this video, it's with the hope to meet again you. They are talking about another type of bonding. It's next time we are going to talk about ionic bonding. Okay students, we are going to finish this video. video. So goodbye.